In this session, we'll be covering some basic data mining algorithm. In practice, most of these algorithms are used with some modification, but nonetheless, they are very important to lay a firm foundation. We'll start with some very basic classification algorithm. Then we will cover statistical modeling, construction of decision trees, and building association rule. Towards the end, we will cover numerical prediction. Then we'll have instance-based learning, and towards the end, we'll be covering clustering. In between, we will also demonstrate how do we practically use Weka to run these algorithms. We'll just be covering 2-3 algorithm in Weka for now, as we have a dedicated session for this. So let's begin. So the first algorithm that we are going to do is a very easy classification algorithm called 1R for one rule. So it basically generates a one level decision tree which tests just one attribute. So what are the steps of 1R? First of all, we consider each attribute in turn. There will be one branch in a decision tree, the one level decision tree which we talked about, for each value of this attribute. So say suppose an attribute outlook has 3 values, so there will be a decision tree for outlook, and there will be 3 branches based on the 3 values outlook has, and will allot the majority class to each branch. So each value of the attribute will cover some of the instances, and the majority class of the instances will be allotted to that branch, and we'll repeat the same step for all the attributes. And in the end, we'll have one decision tree, one level decision tree for each attribute, and we'll choose the one with minimum error. So this is how our algorithm works. Very easy. This is the pseudo code of 1R. So again, we consider each attribute turn by turn, and for each attribute we make a rule or a decision tree, one level decision tree, based on how many branches we have from that attribute, which again will depend on how many values that attribute can have. And for each branch, we'll consider the majority class as the classification of that branch, and by this method we'll have one tree for each attribute, and in the end we'll be taking the tree with the smallest error rate. Okay, for example, we have our weather data, as you can see over here. So again, as you can see, we have 4 attributes over here: outlook, temperature, humidity, and windy. So we will be constructing one level decision tree for each of these attributes based on, and the number of branches in each tree will depend on the values, different values in each attribute can have. So we are considering over here outlook parameter first. As you can see, outlook parameter can have 3 values, 3 attribute value. It's a nominal variable. The 3 values are sunny, overcast, and rainy. Then we have plotted how many number of instances with play equal to no, and then for play equal to yes. Based on this, we have our majority class. For example, in the sunny value, we have play equal to no 3 instances in this case, and for play equal to yes we have 2 instances. So the majority class will be no, and the total instances where outlook equals to sunny is 5. As you can see, 3 plus 2 is 5, and so the error will be 2 by 5. 2 is basically the number of instances where play equals to yes, and this step is repeated for each value of attribute outlook, and in the end the total error is basically the summation of the 3 errors, which is 4 by 14. So when we repeat this with all our attributes, we have the following result. As you can notice, some of the attribute have equal total error. In that case, we can choose any one arbitrarily, and this is how we generate our 1R rule. As you can see, we have a special case when we have missing values. So missing is treated as just another attribute. One branch in the decision tree is dedicated to the missing value, like any other attribute value. So this is how we deal with missing attributes. Then we have the case when we have numerical attributes. So to deal with numerical attribute, we discretize them. How do we discretize them? Basically, we sort all the instances on the basis of this numerical attribute. Then we'll place breakpoints whenever class will change. These breakpoints give us discrete numerical ranges, and majority class of each range is considered as its range, as its class. So for example, we have the following data for weather example. Again, the same data. Here you can see we have two numerical attributes, temperature and humidity. So what we do here, we are going to demonstrate how do we deal with the temperature attribute. So basically, in the first step, we have sorted them on the basis of temperature attributes, and below them we have their classes. And these breakpoint, which you can see, we have a breakpoint whenever the class value change. So when we change from yes to no, we have a breakpoint. Then from no to yes, again a breakpoint. From yes to yes, since there is no change of class, so no breakpoint. And hence we basically divide our numerical data into ranges. The problem with this approach is that we can have a large number of division, or what we call overfitting. Therefore, what we do is we enforce a minimum number of instances in each division. For example, in this case, in this particular case, we have taken the minimum number of instances for the majority class equals to 3. So when we have one yes, no division, then no, again we have no division. And over here, since we have min equals to 3 number of yes, so then we have our division. And you can see the majority class in this division is yes, and the majority class in this division is also yes. And here the number of yes is equal to number of no, so we can take either of them. We'll be taking no. So as you can see, these two adjoining classes have the same majority class. So again, we can combine these two into one set. So in the end, we'll have just two sets. And we have demonstrated this, and from this now we have just two division. And as you can see, this is basically a midpoint between 75 and 80, so that is 77.5. The majority class on the left side is yes, and on the right side we have no. So, and these are the rules which we have. Classification rule: for less than 77.5 we'll consider yes, otherwise we'll consider no. So this is how we deal with numerical attributes in 1R. The next type of classification we are going to study is statistical modeling. We make few assumptions over here, though these assumptions might sound absurd, but they can be assumed. The first assumption is all attribute contribute equally to the decision making tree. So we don't give any kind of priority to any one attribute. Each attribute is considered equal, and all attributes are independent of each other. That is, the value in one attribute is not at all dependent on the value of any other attribute. So these are the two assumptions we make of equality and independence. And moving ahead, we have considered the weather data example only. Just we'll study this table. Here you can see we have our 4 attributes followed by our class. Based on the class value for each attribute, say when class equals to yes, the number of instances, then for class equals to no, the number of instances for each attribute value. And we have done this for each of our attribute. And for the class table, we just have the number of classes with value yes and the number of classes with value no. This is the first part of the table where we have just plotted this data. In the lower half, we have basically plotted this data in the form of fraction. So suppose we take this value 2 by 9. This is basically when we have play equal to yes, then how many instances are there with outlook equal to sunny? The answer is 9. How do we get this? For play equal to yes, we have 9 instances. And out of those 9 instances, how many instances are outlook equal to sunny? 2. So we have 2 by 9. And similarly, we do this with all the attributes and all their values. For the class play, we just have the number of values of class equal to yes upon the total instances, and similarly for class equal to no. Moving ahead. So the upper half showed how many times the value of an attribute occur for a class. The lower half shows the same data in terms of fraction, and we just told you how do we get this fraction. Now suppose we have an unclassified instance where we have the following values: outlook equal to sunny, temperature equal to cool, humidity equal to high, and windy equals to true. So taking our assumptions into consideration that all attributes are equal and are independent, the likelihood of yes equals to this fraction. How are we getting this fraction? As you can see, uh, here what we have done is this 2 by 9 represents the fraction when we have class equal to yes and the cases when outlook equal to sunny. So if we just move to the previous table which we built, here you can see the value is 2 equal to 9. When the class equal to yes and outlook equal to sunny, we have the value 2 by 9. And similarly, considering class equal to yes, we have plotted the value for each and every attribute. So this is for temperature equal to cool, then this is humidity equal to high, this is windy equals to true, and this is play equal to yes. And we have this value. Similarly, we have done for class equal to no. And now we basically need to convert these two fractions into probability. So how do we convert them in terms of probability? We use normalization. So this is how we normalize them, and we have them in the form of fractions. Now the concept which we just used, how do we derive that concept? So basically that concept is based on Bayes' rule. According to Bayes' rule, a hypothesis H and evidence E, we have the following relation. Uh, the probability of having H when we have E, when E is given, is probability of E when H is given into probability of H for divided by probability of E. For our example, hypothesis H is that play will be, say, yes, whatever case we consider, yes or no, and E is the particular combination of attribute values at hand. So E is basically that unclassified instance which we have. Now basically if we have used this notation where we specify outlook equals to sunny. So we have basically divided this this evidence E into four parts: E1, E2, E3 and E4, representing each condition in that unclassified instance. Since E1, E2, E3 and E4 are independent, this is one of our assumption which we have. So the formula for holding of hypothesis when E is given converts to this. Say then for probability class equal to yes. So basically we are assuming that our hypothesis H is yes. We have the following formula, and the only unknown factor in this is P of E. This will be taken care of during normalization, so this factor is removed. And since we are using Bayes rule, so this method is called naive Bayes. Naive because we have the two assumption which we have made, because of that this is called naive Bayes. Now we have some problems with naive Bayes. In suppose we have an attribute value EA for which the probability EA H equal to 0. So we'll just go to the previous slide. If we put that value over here, the whole probability will come equal to 0 irrespective of the other probabilities. We don't want this. So what's the solution? The solution is called Laplace estimator, in which what we do is we basically add few values to the numerator and denominator of each fraction for each attribute. For example, here we have added this new p1, new p2, new p3 in the numerator, and new and new in the denominator. Here p1 plus p2 plus p3 equals to 1. This is the assumption which we have made. This method of this basically, it will increase the each fraction by a fixed amount, and in case we have a 0, it will convert that 0 fraction to a non-zero fraction. Now we will study how do we deal with the missing attributes in statistical modeling. In case a value is missing, say for an attribute EA in the given data set, that is our training set, we just don't count it. We don't include it in our, uh, in the calculation of our fractions, in the calculation of our probabilities. So this is how do we deal with an missing attribute value in the training set. In case if our unclassified instance has a missing value for a particular attribute, so what do we do? For example, what we have considered over here is so that our unclassified instance, the outlook value is missing. So basically, when we are calculating the likelihood of yes and likelihood of no, we don't include the fraction for the outlook attribute. And the rest of the procedure remains the same. The rest of the fractions remain the same. We just don't include the value of outlook fraction. So this is how do we deal with missing attributes. Now we study how do we deal with numerical attributes. Numerical attributes are handled by assuming that they have normal probability distribution or Gaussian probability distribution. We'll consider the case when we have a normal distribution. For a normal distribution, we have the following formula. So basically, this for a particular x, fx is the probability of x. We in the over here, nu is the mean, the sigma, that is the denominator, is basically the standard deviation, x is the instance under consideration, and fx is the contribution of this attribute to the likelihood figure. Now we'll see this in action. Over here we have, as you can see, we have two nominal attributes, temperature and humidity. The rest of the calculations remain the same. For the temperature attribute also, we basically divide all the instances for play equal to yes and for play equal to no. We have the following table. So for play equal to yes, we calculate the mean, then we calculate the standard deviation, and we do the same for play equal to no, repeating the same steps for humidity as well. So now say our instance, sorry. So say when our in our unclassified instance we have temperature equal to 66, so we just put that in our formula for fx, and we have the contribution of temperature equal to 66 in the likelihood. So in the likelihood of yes, we'll just put 0.0340, and we repeat the same for other numerical attributes as well. Okay, so the next thing that we are going to study is the divide and conquer strategy for constructing decision trees. So basically, what are the steps of constructing a decision tree recursively? We select an attribute to be placed at the root and make one branch for each possible value, and then we repeat the process recursively at each branch using only those instances that reach the branch. The third step is if at any time all the instances at a node have the same classification, we stop developing that part of the tree. So it's pretty simple, but the only problem that we have is how do we decide which attribute to split on. So these are the steps to find the attribute to split on. We consider all the possible attributes as options and branch them according to the different possible value for each attribute. Now for each possible attribute value, we calculate information and then the information gain for each attribute. Now in the third step, we select that attribute for division which gives a maximum information gain, and we do this until each branch terminates at an attribute which gives information equal to 0. How do we calculate information and gain? Say if we have the data p1 comma p2 comma p3 till pn such that p1 plus p2 plus p3 till pn equals to 1. So these are basically the different attribute values, and the sum of their probability is equal to 1. The information for this will be minus p1 log p1 minus p2 log p2 till minus pn log pn. The gain will be information before the division on this attribute minus information after the division. and we go for that attribute gives us a maximum information, a maximum gain, sorry. So this is how we actually do it. This will basically help you understand what we are talking about. Here again we have considered the weather data, and we are considering each attribute individually. So here we have our outlook attribute, temperature, humidity, and windy. Okay, so uh, what we have done is outlook can have three values, so we have three branches, and this particular rectangle basically signifies for outlook equal to sunny how many instances have class equal to yes and how many instances have class equal to no. Similarly, for this value of outlook equal to overcast and for outlook equal to rainy, we do this for all the attribute. Here basically we are deciding upon the root node of the decision tree. Now what we do is using the formula for information. Initially we have before any kind of division, we have number of instances with class equal to yes equal to 9, that is 9 such instances, and for class equal to no we have 5 instances. So if we just express them in the form of fractions or probability, we have 9 by 14 and 5 by 14, and the information for them using the formula which we specified is 0.940 bits. So this is basically the amount of information which we have before division. Now we are basically considering the outlook attribute. We observe the following. The attribute outlook can have three values: sunny, overcast, and rainy. Here again we have specified number of class equal to yes and number of class equal to no for attribute value. And basically if you just go to the previous diagram, we are basically considering this diagram as of now. So we are calculating the information contained in each node individually. So we consider this node, then this node, and then this node. In the end we'll be basically take a summation of these three information, and this will be the information which we have after division. So again coming to our table, what we have done over here is again we have taken that each node individually and calculated their information. The node attribute equal to overcast, it contains zero information. As you can see here we have only class equal to yes. So say for example as the final result we go for the division based on outlook attribute, we won't be dividing this branch any further since we have information equal to 0 for this branch. And basically we calculate the information for all the three attribute values, and as you can see we have gain by using, now we are calculating gain by using outlook for division, the information which we have before the division, and we calculate the gain for different attributes over here. So since outlook gives the maximum gain, we will be using it for division. And again we repeat the step for outlook equal to sunny and rainy since the information there is not equal to 0, and stop for overcast since we have information equal to 0 for that particular instance. Now there are some cases where we do have some problem with this divide and conquer technique of building decision tree. One of the problem cases is when we have highly branching attributes. So if we follow the previously subscribed method, it will always favor an attribute with the largest number of branches. In extreme case, it will favor an attribute which has different value for each instance. The particular type of attribute what we call is identification code. So just look at this diagram below. Here as you can see, for each value of this attribute ID code A, B, C till N, we have a different branch. So for each instance we have a different attribute value, and therefore each leaf will contain just one class, and hence the information for each of this leaf will be equal to 0, and hence we have the information gain as the maximum, and therefore our previous method will basically go for this attribute for division. Again, the calculation of information for the previous case, it's equal, hence it will have the maximum gain and will be chosen for branching. But such an attribute is not good for predicting classes of an unknown instance, nor does it tell anything about the structure of division. I mean, it is the case where we have highly overfitting. So to counter this, we use gain ratio. Gain ratio is defined as gain, which we used in our previous case, divided by split info. Now, to calculate split info, for each instance value, we just consider the number of instances covered by that attribute value, irrespective of the class. When then we calculate the split info. So for identification code, like in the previous case, the decision tree which we built, we are talking about this decision tree. So for this decision tree, we had 14 different values, assuming n equal to 14. For this, the split info will be info of 1 comma 1 14 times. So what we have done is, we have just mentioned the number of instances covered by each branch, irrespective of the class value. Say if a branch has one yes and one no, then we'll just have a 2 over here. We are not concerned with the value of classes. And when we calculate this info, it comes out to be non-zero 3.807. uh, for outlook attribute which we considered, the information is 545, since if you remember, for each for the first branch we have 5 classes, for the second we had 4, and then for the third one we had 5. So for the outlook attribute, we have split info of 1.577. As you can see, as the number of branches increases, the split info increase. If the split info will increase, the gain ratio will decrease. And finally, we are going to go ahead with that attribute which has the highest gain ratio. So this is how we basically compensate for highly branching attributes. Now in this table, again, what we have done is, for each attribute we have calculated the gain info. As you can see, for outlook we have the split info at 1.577. Gain ratio is simply the gain divided by the split info. Similarly for the other three attributes as well. And for the highly branching attribute, we have our gain ratio equals to 0.247. So as you can see, again, still the gain ratio of this highly branched attribute is pretty high as compared to outlook, temperature, humidity, or windy, and still our algorithm is going to do a division on this attribute only. But as you can see, the difference between the gain ratio is has been reduced considerably. And we can add additional parameters so that we finally don't do a division on this highly branched attribute. One more thing that needs to be noticed is that the gain of outlook and the gain of humidity differs by quite a amount. But as you can see, the gain ratio are pretty close. This is 0.157, this is 0.152. The reason being is, though outlook gives us a branch which has information equal to 0 and hence having a higher gain, but when we talk of gain ratio, the number of division, the number of branches also play a crucial role, and for humidity we have just 2 branches. Therefore, the gain ratio difference between outlook and humidity is not that much. Now the problem with using gain ratio. In some situation, the gain ratio modification overcompensates and can lead to preferring an attribute just because its intrinsic information is much lower than that of the attribute value. So what we are trying to imply over here is that now gain ratio basically gives a preference to number of division. So it might even favor an attribute which gives a lesser number of division, but the divisions basically have higher information, and hence the division is not very useful. A standard fix is to choose the attribute that maximizes the gain ratio, provided that the information gain of that attribute is at least as great as the average information gain for all the attributes examined. So this is how do we deal with the problem in gain ratio. Coming to our next algorithm is covering algorithm. We just talked about how do we construct decision trees. Now we'll talk about how do we construct rules. So the approach is consider each class in turn, seek a way of covering all instances of that class, and exclude all instances that do not belong to that class. Simple. And identify a rule to do so. So basically what we are trying to do, we are trying to cover all those instances which belong to a particular class, leaving those instances not belonging to that class, and basically converting our approach to a rule. This is called a covering approach because at each stage we identify a rule that covers some of the instances. This visualization will help a great deal. For example, if we have two attribute x and y, and we have two classes a and b, so what do we have over here is uh, basically we have plotted our classes based on these attributes in this two-dimensional plane. And if we do this division, as you can see, all the classes on the left hand side of this division are only class b. So basically we are trying to get a rule for class b over here. We do another division, and as you can see, in this division it's all class b, in this division it's all class b except this particular case, which we can also exclude by further division, and in this division we have only class a. So if you want to derive a rule for class a, then we have the following rule: if x is greater than 1.2, that is the right side of this division, then class equal to a. And if x, basically we are optimizing our rule over here. So the first rule which we derive from this division is that for x greater than 1.2, the class equal to a. So basically we have taken the majority class over here. Now we further improve the accuracy of this rule, and we add the condition and y is greater than 2.6. So basically this particular quarter we are talking about, then class equal to a. So this is a pretty accurate rule which we have. And we've now basically we have left this particular instance of class a. So now if we want to include that as well, what we do over here is, if this conditions remain the same, and we add the following condition: if x is greater than 1.4 and y is less than 2.4, then class equal to a. So this basically covers this instance of class a as well. And these two rules finally give us basically classification rules for class A. We can do the same for B as well. Now we compare rules versus our tree. Now covering algorithm covers only a single class at a time. Like in the previous case, we basically constructed the rule for class equal to A. To construct the rule for class equal to B, we have to run the covering algorithm for class equal to B individually. So basically covering algorithm covers only a single class at a time, whereas division takes all the classes in account, as decision tree creates a combined concept description. Pretty easy to understand. The problem of replicated subtree is avoided in rules. If you remember, we studied a case where we had replicated subtree. That problem is avoided in rule. If we construct the decision tree for our the rules which we derived in our previous case, this is the decision tree which we have. Now we talk of prism algorithm. Now basically we have cleared the concept of covering algorithm. Now how this particular algorithm, prism algorithm, is a simple covering algorithm. Now again, this visualization will help in what we are going to do. Basically we start with a very generic uh, instance division, then we add some rule to make it more specific, and we keep on doing so until we have a required accuracy. Now two criteria to select an attribute for division. So basically while we are running prism algorithm for each class, for each rule we need to select an attribute to make a to add a condition to our rule, or to make a division. So the criteria for that are: include as many instances of the desired class, that is the one which we are trying to get a rule, and exclude as many instances of other class as possible. If a new rule covers t instances of which p are positive example of the class and t minus p are instances of the other class, that is error, then try to maximize p by t. So basically we try to maximize our positive upon number of total instances covered by the rule. This particular ratio, we try to maximize this ratio. For example, we are taking this example data, iris data. We have the following attribute: age, spectacle prescription, astigmatism, tear production rate, and this is our class recommendation lenses. Now we are going to see Prism algorithm in action. So we are going to build rule for the class hard, and we start with the following basic rule, that is, if some condition, then recommendation equal to hard. So here the question mark represents an unknown rule. Now we have the following 9 choices for this unknown rule. Basically what we have done over here is we have taken each attribute, and for each value of this attribute we have basically written over here the p by t ratio, which we talked about for that particular case. So for example, age equal to young, this rule basically covers 8 instances. Out of these 8 instances, only 2 instances have a recommendation equal to hard. We do this for all the attribute value set. Here we notice that the maximum t by p ratio is for astigmatism equal to yes, and basically what we have done, we have choose randomly between equivalent option. In case we have two options which equal t by p ratio, we can take any one randomly. So now our rule is, if astigmatism equal to yes, then recommendation equal to hard. We won't be stopping at this rule, as this rule gives only 4 correct result out of the 12 instances it cover. We are striving towards 100% accuracy, and to do that, uh, we remove the correct instances of the 4 correct instances which this rule gives. We remove those from our instance set, and we modify our rule to this form: if astigmatism equal to yes, and one more rule, then recommendation equal to hard. Now we are going to repeat the whole process again, but as we have just told, we have removed the 4 correct instances from our instance set. So our instance set looks something like this. Mind you, here we have only plotted the cases with astigmatism equal to yes, since this rule has already been added. And moving ahead, the choices for this data are these. Again, their p by t ratio. We choose tear production rate equals to normal, which has the highest t by p ratio of all these choices. So our modified rule is, if astigmatism equal to yes and tear production rate equals to normal, then recommendation equals to hard. We again remove matched instances, and our data has taken the form like this table. As you can see here, all the instances have astigmatism equal to yes and tear production rate equals to normal. We again look at all the options which we have, take the highest t by p ratio, add it to our rule, and do it recursively till we have 100% accuracy. And finally, the rule which we get is this particular: if astigmatism equal to yes and tear production rate equals to normal, and spectacle prescription equals to myo, then recommendation equals to hard. And we do this till all the instances of a class are covered. So we have rules for a particular class, and then we repeat the whole process for other classes as well, taking one class at a time. This is the pseudocode. This basically lists all the steps which we just took. Now we compare rules versus decision list. The rules produced, for example, by the Prism algorithm, which we just started, are not necessarily to be interpreted in order. So basically, they don't follow a particular order. They don't follow a particular order like decision list. There is no order in which class should be considered while generating rules. Using rules for classification, one instance may receive multiple classification or no classification at all. In such cases, go for the rule with maximum coverage. So coverage is basically the number of instances for which the condition in the rule holds true. And for the case when we have no classification at all, and in that case we basically go for the maximum coverage of training example. These difficulties are not there with decision list, as they are to be interpreted in order and have a default rule at the end. So since they are interpreted in order, so this problem of multiple classification is handled, and with a default rule, the problem of no classification at all is also handled. Now we come to mining of association rule. Till now we have looked basically at classification rule. We divert a little and now we'll look at mining association rule. The basic definition of an association rule: an association rule can predict any number of attributes and also any combination of attributes. What are the parameters of selecting an association rule? The coverage, that is the number of instances they predict correctly; the accuracy, the ratio of coverage, and the total number of instances the rule is applicable. So the total number of correct instances they predict and the total number of instances for which the association rule holds. We want association rule with high coverage, and at least it should have a minimum specified accuracy. It should be having an accuracy greater than at least the minimum specified accuracy. We look at some of the terminology. An item set is a combination of attributes. An item is an attribute value pair. For example, for the weather data, we have the table with each column containing an item set. We have different number of attributes. Basically with each entry, basically we are talking about this table. Here you can see we have basically different columns. The first column contain one item set, so basically just one attribute and its corresponding value. This column contains two item sets, so two attribute value pair. Similarly, three item set and four item set. What you see in the bracket is basically the coverage of that particular rule. This table is not complete. It goes until quite a lot of rows. This basically gives a general idea of how it will look. Now we come at actually generation of association rule. We need to specify in the beginning, we need to specify a minimum coverage and accuracy for the rules to be generated beforehand. So these two parameters should be there when we start working. Now the steps for generation of association rule: generate the item set. By item set, which we mean basically this table. Now each item set can be permuted to generate a number of rules. For each rule, check if the coverage and accuracy is appropriate. That is, they are greater than the minimum specified coverage and accuracy. And this is how we generate association rules. Pretty simple. We'll look at an example. Say for humidity equals to normal, if you take this item set, so this is basically a three item set. If you go to the table, we are talking about three item sets over here. So we take this item set: humidity equals to normal, windy equal to false, and play equal to yes. If we permute these three, we can have 7 potential rule for humidity equals to normal and windy equals to fall, and then play equal to yes. And then these are the other rules which we have. The last one is, if anything, then humidity equals to normal and windy equals to fall and play equal to yes. What you see over here is basically the accuracy. The numerator is basically the coverage, and denominator is basically all the instances which it covers, whether they are true or not. So these are the 7 potential rules which we have. And basically we can take we can select any number of rules from here, provided they follow they give us a minimum coverage and a minimum accuracy, which we mentioned in the beginning. So this is how we generate association rules. Now we come to linear models. In linear model, we'll basically look at two things. We'll look at methods to deal with the prediction of numerical quantities. Till now, we were just talking about the classification, then we did association. Now we'll talk of prediction of numerical quantities. We'll also see how to use numerical methods for classification. So let's begin. Sorry. To do numerical prediction, the technique which we use is called linear regression. Linear regression is basically again a technique to predict numerical quantities. Here we express the class, that is a numerical quantity which needs to be predicted, as a linear combination of attributes with predetermined weights. So if we have the attributes k attribute a1 to ak, and the class to be predicted is x, so x is represented in this form where w0, w1 to wk are basically the predetermined weight. So we have w0 plus w1 into a1 plus w2 into a2 till wk into ak. So if we have the weights w0 to w1 till wk, then we can easily, and since a1 to ak, this we will get from the instance which needs to be predicted, so we can have the predicted value of x. How do we determine these weights? The weights are calculated by using the training set. So basically they involve some matrix operation which we won't be covering over here, but the parameter that is used to choose the optimum weights is that we try to minimize this square sum. If you look at this x raised to the power I is basically the actual value of x in the instance I. This is the actual value, and this summation is basically the predicted value. This is basically the representation of this formula only. So basically what we do, the actual value minus the predicted value, we take the square and we sum all these value for all the n instances, and the weights which we choose basically try to minimize this. Now we come to that was linear prediction. Now we come to linear classification. For linear classification, the technique which will be dealing with is multi-response linear regression. In multi-response linear regression, for each class we use linear regression to get a linear expression. That is just like in the previous case, but now when the instances belong to a class, the output is 1, otherwise 0. And for all the unclassified instances, so basically let's come back to the equation. So we have this equation which we use for prediction. We'll be using the same equation for classification as well. What we do is we take one class, right? We take each class turn by turn, and we consider all instances for that class. So basically, if an instance belong to a particular to the specified class, the value of x is 1. Otherwise, it's 0. So basically, if we have n instances, and so for each for each class we will have n such equation. From those n such equation, we'll determine these weights, and therefore we'll have one equation for each class. So if we get an unclassified instance, we use the expression for each class. We basically put the value of attribute a1 to ak of this unclassified instance in the equation, in the expression for each class, and we get a output for each class. Now the class expression giving the maximum output is selected as the classified class. So this is how we do classification using multi-response linear regression. Now the problem with this is that the values produced are not proper probabilities. As you can see, we are basically going ahead with the maximum output, and we are not actually getting any kind of probabilities. The probability basically lie in the range 0 to 1, and over here the output which we consider the maximum output might or might not lie in the range 0 to 1. So we are not getting actual probabilities. To solve this problem, we use a technique, again for linear regression, we use a technique called logistic regression. To get the output as proper probabilities in the range 0 to 1, we use linear logistic regression. Here the output y is defined as 1 upon 1 plus e to the power minus x, and x is given by this equation. So basically, if you look at this expression of y, the output of for any value of x from minus infinity to plus infinity, the value of y will always lie in the range 0 to 1. So all the steps of multilinear response remains the same, but now the final output is represented as y and not x, and y is given by this expression. The Basically in multilinear response, in the uh, prediction case, we try to minimize the square sum. For logistic regression, we have a different parameter which we want to will maximize this parameter. This is the value which we want to maximize. To generalize a logistic regression, what we can do is we can use the calculation like we did in multi-response linear regression. In case we have more than one classes, so we can use that technique. Again, the problem with this approach is that the probability of different classes do not sum up to 1. So the output, coming back to the previous slide, the output y will lie in the range 0 to 1. But we don't know whether, if we just add the value of y for different classes for a unclassified instance, the sum might or might not come equal to 1. So they are not actual probabilities, though they lie in the range 0 to 1. The other technique of linear classification is using the perceptron. If instances belonging to different class can be divided in the instance space by using hyperplanes, they are called linearly separable. So what we are trying to do over here is, if you consider all the instances which we have belongs to a instance space. It might be a two-dimensional instance space, three-dimensional, or whatever dimensions might be. If somehow we can divide that instance space into different parts by using hyperplane, such that each part has a particular class and no other class in it, then these instances are called linearly separable. If instances are linearly separable, then we can use the perceptron learning rule for classification. The steps for using the perceptron learning rule is, we are considering that we have only two classes. uh, the equation of hyperplane is this. Basically what we have done over here, if you remember, this equation is very similar to the equation which we used during the prediction and during the classification for x. So we have the same equation, but we have equated it to 0. This will give us a hyperplane. With w0, basically we have included the attribute a0. Its value will remain to be 1. So this is the equation of hyperplane. If the sum mentioned in the previous step is greater than 0, so basically when we talk of sum, we are talking about this expression, this left hand side of this equation. So if the sum is greater than 0, then we have the first class, otherwise the second class. So basically this is how we do the classification. Of course, to do the classification, we need to have the values of weights w0 till wk. How do we calculate those weights? We'll look at that now. The algorithm to get the weight, and hence the equation of dividing hyperplane is, this hyperplane is basically called the perceptron, hence the name perceptron learning rule. What we do is we set all the weights initially to 0, and we repeat these steps recursively until all the instances in the training sets are classified correctly. uh, for each instance I in the training set, if I is classified incorrectly by the perceptron, say if I belongs to the first class, I put the value of attributes of I in the equation which we talked about over here, and its value is less than 0, whereas it should be greater than 0 since it belongs to the first class. So therefore it's not classified correctly, that is, it's classified incorrectly. So what we do is, basically we take the attributes of I and we add it to the weight vector. By weight vector we mean the vector w0 comma w1 till wk. And suppose if I if belongs to the first class and it's classified incorrectly, then we add it to the weight. Otherwise, we subtract it from the weight, and we do this for each instance I in the training set, and all of these steps are repeated until all the instances in the training set are classified correctly. So this is how we deal with the numerical prediction and numerical classification. Next thing we are going to cover is instance based learning. This is again a way to classify unclassified instances. The general steps is no pre-processing of training set. So we don't build a decision tree, we don't build decision rules, so there's no pre-processing of training set. We just store the training instances as it is, no modification, no pre-processing. Now to classify a new instance, we calculate its distance from every stored training instance by some matrix. We'll talk about this later. Now the unclassified instance is allotted the class of the instance which has the minimum distance from it. So basically from all the weights which we calculated in step 2, uh, to classify this unclassified instance, we use the class of that instance which is nearest to this unclassified instance. Now how do we calculate distance between between a instance in the training set and an unclassified instance? The distance function which we can use is it belongs to it basically depends on our application. Different application For different application we have different distance function. Some of the popular distance functions are Euclidean distance, which we are going to demonstrate. Then we have Manhattan distance metric and many others. The Euclidean distance is given by this formula. Basically this is the square root of square but in this bracket what we have done over here is, this is attribute a1, the value of attribute a1 in one instance. This is the same attribute in the other instance. We take the difference, square it, and we do this for all the attributes, add all of them and take the square root. Here k is the number of attributes, and this is how we get the Euclidean distance between two attributes. Sometime we need to normalize the data. We normalize attribute such that they lie in the range 0 to 1. We use this formula where vi is the original value of attribute. We subtract the minimum value from it and divide it by the maximum value of the same attribute minus the minimum value, and we store it in AI. So this is the normalized value of attribute vi. Now how do we deal with missing attribute? In case of nominal attribute, if any of the two attribute, that is by two attribute we mean the two attributes belonging to the two instances of which we are trying to calculate the distance. If any of the two attributes are missing, or if the attributes are different, then the distance is taken as 1. For nominal attribute, if both are missing, then difference is 1. If only one attribute is missing, then the difference is either the normalized value of the given attribute or 1 minus that size, whichever is bigger. So in case of missing attribute, we basically try to maximize the distance by taking the maximum value. Now how do we find the nearest neighbor? We have the distance of an attribute of an unclassified instance with all other instances belonging to the training set. Now how do we find the nearest neighbor efficiently? We can the trivial way will be to just calculate all the distances and just select the minimum one. That of course consumes a lot of time, so we want an efficient way to do so. We do this by using a data structure called k-dimensional tree. K-dimensional tree are binary trees that divide the input set with a hyperplane and then split each partition again recursively. It stores the points in k-dimensional space. By points we mean basically the instances belonging to the training set, k being the number of attributes. So the number of dimensions, dimensional space, the number of dimensions in the dimensional space it will be using will be equal to the number of attribute it has. So now we'll look at how do we find nearest neighbor efficiently. This is basically a k-dimensional tree. Here we have considered just two attributes, so it will divide the instances in two-dimensional space. The h and v you see over here are basically the axis along which the division is being done. This is just an equivalent representation of this k-dimensional tree. This axis belongs to a1, this is a2, the root node is 7 comma 4, and the division is done along the horizontal, parallel to the horizontal axis. So basically we are talking about this line, and so this divides it into two parts. On one part we have 2 comma 2, which we don't further divide into any further hyperplace, and on the other side we have this following 2 points where we again do a division on 6 comma 7 parallel to the vertical axis. How do we do this division, and at what point do we do the division, we'll be looking later. We'll first talk about, if we have our k-dimensional tree, then how do we find the nearest neighbor efficiently. So this basically talks of the example which we just see here. We saw a k-dimensional tree and the instances with k equals to 2. As you can see, not all child nodes are developed to the same depth. So as you can see over here, 2 by 2 just ends over here, whereas we have developed this node 6 comma 7 further. Also we have mentioned the axis along which the division has been done, that is v or h in this case, since we are talking about only 2 dimensions. Now the steps to find the nearest neighbor. The first step is to construct the k-dimensional tree, which we talked of later. How do we construct the k-dimensional tree? Now given an unclassified instance, we start from the root node and compare the appropriate attribute and move to either to the left side or to the right subtree. Now basically the root node is compared with the unclassified instance based on a appropriate attribute. Now which attribute which we need to compare is based on the axis along which the division has been made. For example, if we have this decision tree and we are basically comparing our unclassified instance to this node, the division has been made along the vertical axis, that is this axis. So we'll be comparing basically the attribute a1, and say if we talk of this node, here we'll be comparing the attribute of this node with the a2 attribute of our unclassified instance. So basically the attribute which we need to compare depends upon the axis along which we have made the division. Moving ahead, the next step is repeat this step recursively till you reach a node that is either a leaf or has no appropriate leaf node. So again, coming back to the tree, so say we start from here. For example, we start from here, we come over here, and we reach over here. Now this is a leaf node, we stop over here. Now you have find the region to which this new instance belong, and you also have a probable nearest neighbor in the form of the region's leaf node. We'll explain this. Okay, so again we'll come to this tree. So we started from this tree, this node, we come to this node, and we reach this leaf node. We stopped over here. So basically we are in this region right now. So our unclassified instance can be anywhere in this region. So at this particular instance 3,8 is a probable. We are not sure whether it's the absolute, but it's a probable nearest neighbor to our unclassified instance, and the distance of our unclassified instance from this probable nearest neighbor is the probable nearest distance. So any other attribute which might be the actual nearest neighbor to our unclassified instance, it should belong to a circle with this radius. Say for example our instance is basically there at the point which I am pointing. Our probable nearest neighbor is 3/8. This distance is our probable nearest distance. So with this center, we construct a circle with this radius, and if this is not our absolute nearest neighbor, then whatever the absolute nearest neighbor it will be, it will belong in this circle, equal to this distance. Okay, now we'll move now we will redo our recursive trace. So we'll till now we basically traced down the tree. Now we'll move upward, looking for an instance which is closer to put which is closer to our unclassified instance than the probable nearest neighbor we have. We to look at the instances, we start with the immediate neighbor. If it lies in the circle, then we will have to consider it and all of its root node, if any. If that is not the case, then we check the sibling of the parent of our probable nearest neighbor. We repeat these steps till we reach the root. In case we find any instances which are nearer than our uh, probable nearest neighbor, we update the nearest neighbor. So basically, this diagram will help it explain in a better way. This star represents our unclassified instance, and by following our first few steps, we have reached to the conclusion that this star, this unclassified instance, belongs to this particular region, and the black dot over here is the probable nearest neighbor. Now, using this as the center and the distance of this star from this dot, we have constructed this circle, and if there is any other neighbor which is closer to this star, then it will definitely belong to this circle, and we will have to consider all the region which this circle intersects. So the first region with that we will be so we'll basically how in what order do we consider the region, will recursively move upwards the tree. So the first region that we will be considering is uh, the star belongs to this region. This particular shaded region is the sibling of this region. So the first region that we consider is this region. As we can see, this region does not intersect this circle, so we cannot have a nearest neighbor to this region. The next region which we will use is the sibling of the parent. So basically, we are talking of this complete region above this horizontal line, and out of this we again we have this division divided into two parts. Out of this, we should not consider this part as the circle does not intersect this part, so we'll consider this part. Now this part does have a instance which is more nearer to this star as compared to this black star, and we basically point this instance as the nearest neighbor. We repeat these steps until we reach the root node. In this particular case, this will remain to be the nearest neighbor, and this is how do we find the nearest neighbor using a k-dimensional tree. Now we come to the construction of k-dimensional tree. To construct the k-dimensional tree, we need to figure out two things: along which dimensions to make the cut and which instance to use to make the cut. Now deciding the dimension, how do we decide the dimension? We calculate the variance along each axis. The division is done perpendicular to the axis with minimum variance. And deciding the instance to be used for division, we just take the median as the point of division, and we repeat these two steps recursively till all the points are exhausted. So if we come to the decision tree which we saw over here, okay, so in the beginning we have all these instances 7 comma 4, 2 comma 2, 6 comma 7 and 3 comma 8. So what we do is we calculate the variance along this axis and along this axis, and based on the axis which has the maximum or higher or lower variance, we do the division. Over here we do the division along this axis. Now we know that we need to do the division along an axis which is perpendicular to the A2, but which point to use? So basically we take the median of all the points which we have, that is 2 comma 2, 7 comma 4, 6 comma 7, 3 comma 8, and we do the division along the median of all these points, that is 7 comma 4 in this case. and we do this recursively till all the points are exhausted. Now the next thing that we are going to cover is clustering. Clustering techniques apply when, rather than predicting the values, we just want the instances to be divided into natural groups. So basically we are looking at the division of instance space. Now iterative instance based learning, the first algorithm of clustering which we are going to do is k-means. Here the k-means, the k represents the number of clusters. So the according to the value of k, the instance space is divided into k clusters. K-mean forms the clusters so as the sum of square distances of instance from their cluster center is minimum. So this is the end purpose, or this is the uh, basically the matrix on which we do k-means. Basically we try to minimize the sum of squares of distances of instances from their cluster center. Now the steps of now we will look at the steps of clustering. The first step is to decide the number of clusters, that is k, manually. Now from the instance set to be clustered, we randomly select k points. This will be our initial k cluster center. So from all our instances, we randomly select k points and we will take them as our initial k clusters center. Now take each instance in our in the set basically in the set which we need to cluster one by one. Take each instance and calculate its distance from all the cluster center one by one, and allot it to the cluster for which it has the minimum distance. Once we have all the instances have been classified, take centroid. So basically all the instances have been clustered into different clusters. Now we consider each cluster individually and we calculate the centroid of all the points belonging to a cluster, and we calculate the centroid of all the clusters. This centroid will give us the new cluster center. Now we'll use this new cluster center and we will repeat these steps. Take each instance, calculate its distance from this new cluster center and allocate it to the cluster center which has the minimum distance from it. And so basically we'll have our clusters, we'll again have k clusters. Now we'll again calculate the centroid and repeat these steps. We are going to repeat these steps until our cluster centers keep on changing. Suppose if in two consecutive steps our cluster centers don't change much, then we stop at this, and the k clusters at this point give us our k clusters. So this is how we do k-means clustering. So in this session, we covered the basic algorithms. We did basic algorithm regarding classification, starting from the very simple 1R to more complex one. We also learned how do we build decision trees, decision rules. Then we move on to association rules. Then we did numerical prediction, and in the end, we also covered k-means clustering. Now, as we told you in the starting, we are going to demonstrate few of the algorithms that we just did. So okay, so this is basically the explorer part of Weka. We choose our input file. We are going with the weather data. We import the weather data to Weka. Now first of all, we are going to demonstrate the 1R algorithm. That is the first classification algorithm that we studied. So we move on to the classify tab. In the classifier, we the 1R algorithm basically belongs to the rules subset of classifier. From here we select 1R and then we click on start. The test option, we have basically selected cross validation with 10 folds. We can do further manipulation by using this more options button. We are going ahead with the default values, and then we click on start, and here you go. The clustering has the classification has been done as we did in our example. Over here also the classification has been done on the basis of outlook attribute. Below this we have all our error matrices. We have our kappa statistics, mean, absolute error. Some of these things we are going to study in our future sessions, and this is how we did do 1 hour. Now we are going to demonstrate, let's do naive Bayes. So naive Bayes belongs to basically this Bayes subset and classifiers. We select naive Bayes, and we again go with the default setting, and we click on start. And here you go, you have the results for naive Bayes. As you can see, for numerical attribute we have the standard deviation, mean, etc., which we need when we are dealing with numerical attribute, and again all the error matrices, and in the end we have our confusion matrix. So this is how we do naive Bayes. The other algorithm, they're more practical implementation, we are going to deal with in our future sessions. For now, we just wanted to show how do we use Weka to implement all these algorithms really easy, in a really easy way. So this brings us to the end of the session. Thank you.